Hello guys and welcome back to Leet Logics. This is a Leetcode hard, but I am sure that if you watch the video till this end, it will not be a hard problem for you anymore. So today we are going to tackle the number of ways to stay in the same place after some steps. And in this question, we are given with a pointer which is starting at index 0 and we are given an array size that is ARR length and you have to make steps, and with each step we can move one position to the left, one position to the right, or or we can stay at the same position, but we cannot move outside the array. And our goal is to find the number of ways in which we can the pointer can be still at the original place uh, after exactly k steps or the steps given in the question. So we have to find we'll ensure that the result is in modulo, so we'll use a mod because it is written in the question to use them. So let's take the sample example one. We are given with steps equal to 3 and array length equal to 2. So number of ways in this in which we can stay at the same position is 4. And if you ask it how, then you can see we have 4 different ways. In the first way, you can first move to the left, then move to the right, and then stay. In the second way, you can stay, then move right, and then move left, then also you are at the same position. Or you can move to the right, stay at right, and then move left, you come back to the original position. Otherwise you stay in all the 3 steps, so you still be at the same position. So the basic approach which, or the naive approach which we thought of after seeing the question was the recursive approach. We can explore all the possible combination of moves, and by moving right, left, or staying at the same position and recursively calculating the number of ways, we can end up at index 0 after steps. So this approach will help us to understand the problem better, but it is not an efficient approach. I have tried it and I have got a time limit exceeded error on this approach. So let me just explain you the recursive approach. So first of all, in the recursive approach, let me tell you the base cases. The base cases is that if you move out of the array, that is your position is less than 0 or your position is greater than equal to array length, then you will simply return 0, that this is not a possible way. Otherwise, if you exhaust your steps, if steps equal to 0, then you check if the position is 0, that means I am still at the same place where I started, then you will return a 1, otherwise you will return a 0. And this the ones you are returning, they get accumulated and they constitute the entire answer for the solution. So you can see the flow chart, what will it look like. So if steps is greater than equal to 0, you can move left. In this case, position equal to -1, you can stay at the same location. In this case, there will be no change in the position. Otherwise you can move right, then there will be a position increment in the position. But the problem is that this approach is highly efficient. And why? Let me tell you why it is highly efficient. You can see there are a number of overlapping subproblems in this case. Like for 0, 0, 4, you have 1, 2. Then when you will call by moving right and steps equal to -1, that is 1, 3, you will again encounter the subproblem 1, 2, and then you are calculating 1, 2 is for 2 times, and the smaller subproblems are repeating multiple times. You can see 1, 1 is 1, 2, 3, 4, 5 times, and it still has to go on. So there are a number of overlapping subproblems, and this is a simple example, a simple test case by which state chart is drawn for. If we take a larger example, it will be a huge problem. So what we want to do is that we want to reduce the number of overlapping subproblems. So we'll find a way to do that. So first of all, look at the recursive code, because this will help you to understand the logic. So in this, we have called the custom function which we have made. The custom function takes a steps, the position, and the arrow length. Initially, we are given the steps as same as the steps given in the question, and arrow length same, but we have kept the position equal to 0. Now, what we have to do, if position, as I talked about you, the base cases, if position is less than 0, or the position is greater than ARR of length. That means we have moved outside of the array, simply return 0. Otherwise, if steps equal to 0 and we check, we have exhausted our steps, and also the position is also 0, which means we started at the position 0 and we are still at position 0. This means this is a possible way. So we add 1, we return 1. Otherwise, what we'll do, we'll call for left, right, and at the same position. So first of all, we have defined int ways. We reduce the steps by -1. We do not move the position, that means we are staying at the same location, and we have given the length. Then next we add by moving left, because we have done a position left, so we move left and add the number of ways and the ways, and then we move right and then add the number of ways in the ways. So this is the basic recursion or the naive approach. But now we need to reduce the number of overlapping subproblems. So how we will do this? So we'll use a DP array to minimize the overlapping subproblems. And what we will do is that for every pair of steps in position, there will be a location in the array, and if we have calculated that uh, the subproblem for that particular steps and position, we'll store it, and the next time we encounter the same subproblem, we'll not do the calculation again, but we'll simply return the answer from the previous subproblem. So this is the memoized solution for the recursive approach. We have taken a 2D DP of array length and steps plus 1. We are filling it with -1 because we want to check if the solution exists or not. So first of all, we do the same thing. We check if there is already we have done the calculation for the particular pair of position and steps. We simply return the previous calculation. Otherwise, we do the calculation. We first of all will move to the left, then we move to the right, and then we can share the same position as well in this case. So, and otherwise, after all you have done all the calculations, store it in the DP and simply return the number of ways. So this is a memoized code. You can take a screenshot if you want. This is a highly efficient approach. You can see it gives excellent runtime, beats 100% almost, and beats 95% in space as well. So this is, you can say, this is a very highly efficient approach. Now, if you are in an interview, the interviewer might expect a more elegant approach to this question, or he may ask you to optimize the space used by the DP array. So in this case, you can use a bottom-up DP. In this, you can see we have started from the steps equal to n given, but from the right end you are starting. But in the bottom up, you start from steps equal to 0 and you build the entire answer up to the steps required. So let's have a look at the bottom up DP as well. So in this, you take a DP. Initially I took a 2D DP, but later I have optimized it into a DP of size 1, because you can see this is a constant already. We have only 2 rows, so you can treat it as a 1D DP only. So first of all, do the 0 of 0 equal to 1, because staying at the same position is a possible way of getting the position same. Then what you will do is that we'll iterate through the steps and we'll iterate through the columns which we can move. So you can say I have used an approach of using a mod, so that I will alternatively use the rows of the DP array. For the for the 0th index, the 0th will be the current and the 1 will be the previous. While for the first index, the 0th will be the previous and the first will be the current. So similarly, it will go on for all the I values, and you can see in this we can either stay at the same position, otherwise we can move left. We are moving to the left, otherwise we can move to the right. So this is a bottom-up DP. You can take a screenshot of this as well. This is a more space optimized approach to the previous approach, and the interviewer might expect this solution from you as well. But if you can do it up to the memorization part, it is also a good approach. I mean, it is also good. So let us talk about the time complexity for these. So the time complexity for the recursive approach, for which I got the time limit exceeded, is 3 raised to the power steps, because for each uh, uh, recursive call we are calling 3 times, staying at the same position, moving to the left, moving to the right. So there is exponential time complexity 3 raised to the power steps. For approaches 2 and approaches 3, that is the top down and the bottom up, we have the time complexity of steps into array length, and the space complexity is for approach 2 is steps into array length as well, because we are using a 2D array, DP array. But for the space complexity for the third approach, that is the bottom up, it's a linear. We are using space complexity O of array length, you can say. So this was my solution for today's question. Please do like the video, share it to your friends, and subscribe to the channel. My current subscriber to my channel are 67, and I hope that by the end of this video I reach 100 subscribers. So thank you for watching this video. Have a nice day, and let's meet tomorrow again and solve our new question together. Thank you.